Hi, so I'm going to give you a brief overview of the similarity solutions to the thermal boundary layer, okay? And yeah, so without going into too many details, but I think this is important so that you have this information at hand, right? That yeah, so how basically do we use the similarity solutions to similarity variables? How do we use the concept of similarity to get some solutions to the thermal boundary layer? Okay, so let me call this as similarity solutions, right, to the thermal boundary layer. Okay, now we've talked about the Reynolds analogy earlier, right? So I'm going to sort of pick up from there. Okay, and now from the momentum equation which we have written earlier, so we can write this. Hopefully you can recall. Okay, so for the momentum equation, okay, so let's write that. So momentum equation. So we can write this. Okay, and the energy equation okay. Okay, I'm just reproducing these two equations right here. Okay, now what we'll do is we'll look at several cases and what should be the specific values of these constants there and possible solutions. Okay, that's what we're going to do right now. Okay, so number one is boundary layers with the wall. Okay, so okay, boundary layers with the wall. So in this case, the first that we go to is Reg flow. So here alpha 1 is 1, alpha 2 is equal to alpha 3 is equal to beta, alpha 4 is n into 2 minus beta. Okay, so then from 2 what we get right, from the equation 2 what we get is alpha 1 is 1, okay, f theta dash minus alpha 4 is n into 2 minus beta, okay, but we have seen that, okay. So yeah, so we can write basically the connection between Mn and beta, right? So we can write that, so 2n okay, alpha 4, okay, f dash theta. Okay, so basically we just write out beta, right? This and that is equal to 0, okay? And the boundary conditions then become, now eta is 0, theta is 1, okay? Eta is very large, theta is equal to 0. Okay, so in this case now, okay, what we will do is we will, in this case, right, we will write, so, you know, the velocity in terms of the local x, you know, coordinate, and the thickness, boundary layer thickness, zeta to the power 1 minus m by 2, right? Now, these are some of the things that we've used earlier, so please, you know, just remind yourself, and if you go back into the notes, you should be able to see everything. Okay, I'm not repeating what we've done before. Okay, so that, now then, okay, and of course, Reynolds number, right? Therefore, from this consideration, we obtain by under root Rex, okay, is equal to m plus 1 by 2 this, right? And for the standard boundary condition, right? Now, for standard boundary condition, so a flux of the wall is constant, so that, right, is equal to this, right? So we get n is equal to 1 minus m by 2. N is equal to 1 minus m by 2. So that is the that's basically for the wedge flow. Okay, so this is for the wedge flow. Now, then the next thing is we will with the wedge flow. Now, the wedge flow in reverse. Okay, so reverse wedge flow. So let us see, how does that look like? Okay, this is so this is wedge flow in reverse. Okay, in this case, okay, in this case, so alpha 1 is minus 1, alpha 2 is alpha 3 is equal to minus beta, alpha 4 is minus r 2 minus beta. Okay, so that's that. Okay, so that is that. The next thing is flow in a convergent channel. So the next thing is flow in a convergent channel. Okay. So, alpha 1 is equal to 0, alpha 2 is equal to alpha 3 is equal to 1, and alpha 4 is equal to minus r. Okay. Moving flat plate. Okay, if you had a moving flat plate, so alpha 1 is 1, alpha 2 is alpha 3 is 0, okay, and alpha 4 is is 2r. Okay, and then again wall jet. Okay, so alpha 1 is 1, alpha 2 is 0, alpha 3 is minus 2, alpha 4 is 4 times n. Okay, so that's basically to give you an idea as to, this is basically, so if you can see that, finally it boils down to, solving this equation. And if you do have, if you have a ready-made code, you can actually basically be able to handle a lot of these cases, isn't it? So at least, all you need to do is change the alpha 1, these constants, right? Of course, the nature of the numerical solution also changes, and that's for something that, that's something to, and the point here is that you may or may not need, right? You may or may not need all of these things. You might just do a wedge flow, or maybe just a flow in a convergent channel, or say, for example, a moving flat plate. You might just do one of these, okay? Any one of these, or maybe a little more of these, or maybe all of these, who knows. But this is so that, just to give you an idea as to, like we were changing, the other day when in the model, when we took the equation and we put in different values of beta, and we were seeing how the solution was changing. So that basically also means that, the value of, when you change the value of beta, so you're also looking at different physical flows, right? So, because the code itself, the code doesn't know, right? Code just treats the beta as just any number. So you're just changing a number and it's giving you a velocity profile. But you can make the inferences that, okay, so if I make this beta that actually physically corresponds, for example, if I have beta, beta is equal to, say, -1 here, or beta is equal to 1. So that alpha 2 and alpha 3 is equal to -1. This is wedge flow in reverse, right? So whatever velocity profile that I get, right, that corresponds to physically a wedge flow in reverse. Okay. So now the next thing is, this is without a wall, right? So that's interesting, right? What do you mean by, there's a boundary layer which is forming and there's no wall, okay? So let us see. So boundary layers without a wall, okay? So boundary layers without a wall. Okay. A mixing layer. Right? So basically we have two things here. One is a mixing layer and the other is the free jet. So that's all we basically have here. Now for the mixing layer here, so we've got alpha 1 to be 1, alpha 2 is equal to alpha 3 is equal to 0, and alpha 4 is equal to 0. Okay, and with the following boundary conditions. Okay. One, right, and this is the temperature difference between two parallel jets. Isn't that right? So basically what you see here is that, you've got a mixing layer. So what does your computer code do? The computer code, you just tell your computer code that, alpha 1 is 1, alpha 2 is equal to alpha 3, which is equal to 0, right? Alpha 4 is 0. So now what you could basically do is look at the equations here, right? Okay, look at the equation here, put in those values and see what the equation reduces to, right? That's what we're talking about here. So you need the velocity field and you also need the temperature field. So you need the velocity field, it's like a forced convection thing, right? Okay. Right. So the computer code basically understands that you're giving it some values for the constants, alpha 1, alpha 2, alpha 3, alpha 4, right? Now then you give it the boundary condition saying that, so if eta goes to the negative side, far off on the negative side, theta is 1, okay, and theta is 1, and if it goes on the positive side, right, it goes positive on the far side, theta is 0, okay. So theta here, did we kind of write down? Well, so theta is your non-dimensional temperature difference, right? So what we basically see is that, so there is a temperature difference between two parallel jets, right? So you go from one end to the other end, right? So that is your eta, right? You go from one far end to the other far end, right? And your non-dimensionalized temperature difference goes from 1 to 0. And this delta TR is basically the temperature difference between two parallel jets, okay? And the next thing is 2.2, okay? We're going to talk about free jet. So this is a free jet, right? So in this case, alpha 1 is 1, right? So this is a free jet, okay? And these are the values of the constants, right? Now, if the fluid on each side of the free jet has a different temperature, then the boundary conditions become so. Let us see. Now, in this particular case, now if the fluid on each side of the free jet has a different temperature, the boundary conditions, are the following. So the boundary conditions are, you go to the far, negative side, so your non-dimensional temperature difference is 1, and if you go to the positive far off side, right? So if the fluid on each side of the jet has a different temperature, right? So obviously this will hold for that, and this is satisfied. This is satisfied for n is equal to 0, right? And in addition, now in addition, to this, right, so this is, well, basically satisfy n is equal to 0. Now, in addition to this, okay, for n is equal to minus half, you know, if you have an n is equal to minus half, the general solution raised to the Prandtl number, right, and this is called, right, eigen solution okay, for the hot free jet. Right. So, this is general solution, okay. So, in case you have n is equal to, n is minus half, and this is called the eigen solution for hot free jet, okay. And the final thing that I would like to say on this is that thermal energy, of course, the thermal energy in the free jet must be independent of the distance along it. So let me sort of emphasize that a little bit. So now thermal energy in the free jet okay, must be independent okay, of the distance along the jet. Okay, so thermal energy in the jet must be independent of the distance along the jet. Okay, so that's really everything that I really wanted to talk about in terms of, you know, the similarity solutions to the thermal boundary layer. So this is basically an overview. So for students who are going to be, you know, who are going to research on this, there are several of you who've enrolled saying you're in master's program, PhD programs, and who want a future in this. So this is to give you an idea that when we do, you know, see the basic equations and we develop the similarity solutions, right? Because I don't want, because there's a lot of math involved. There is a lot of math involved, and we've also some of the math is also quite rigorous. Okay, and it is slightly complicated. I won't, I will acknowledge that, but I think hopefully slowly you begin to see the pattern, right? Hopefully you begin to see the pattern that once you get the basic, equations in place, right, and the effectiveness of the similarity solution. So you break this equation down, the similarity solution down. So, and you have one for the momentum equation and one you have for the energy equation. So you need both of those for the thermal boundary layer, of course, right? So in order to predict the temperature fields, you need the velocity fields. So you're using both, isn't it? So now once you do that, okay, you take this and then you basically change the values of the constants, right? You change the values of the constants, and what you get out of it is that you get different equations. You get different equations for different cases, right? So one, we have this wedge flow, right? We had 5 of these. We have a wedge flow in reverse, we have a flow in a convergent channel, we have a moving flat plate, we have a wall jet, right? Now, the difference between all of these things as far as the computer code is concerned is just the difference between alpha 1, alpha 2, alpha 3, alpha 4, beta, Mn, whatever. So it's just those. Now you kind of take that, right, and feed it into your computer code, right? And then of course, you know, when the moment you give different values of these constants, your equation also changes, right? So it will also kind of give you a different numerical nature of the equation, right? But once you've got, you know, the Runge-Kutta method in place, right, and you are able to solve, you know, these things over a certain domain, and to define that domain, what you need is a boundary condition. So if, for example, for the wedge flow, we had a boundary condition where the eta went from 0 to infinity, right? So 0 is basically at the wall, right, where the velocity, the thermal non-dimensional temperature difference is basically 1, okay, and in this case there is none, because this is the, because the temperature is equal to the free stream, so there is no difference. So that basically tells the computer code, you know, the computer code is basically solving two equations between the boundary conditions, right? Now what you get out of that for you to make the inference, so you should know that when I use these values and I use these boundary conditions, what I come up, the solution that I get physically corresponds to a wedge flow, right? So, I mean, my request to you is not to get flustered with all the math and a lot of derivations. It is important, I mean, I could not do these, right? So if I've bored you a little bit, I apologize, but, you know, if I don't sort of, you know, do this, I don't know how else to do this, okay? So, so I'm just basically trying to impress upon you that if you have a basic, you know, generic computer code where you keep the computer code in terms of alpha 1, alpha 2, alpha 3, right? Keep it in terms of that, and then the moment you change this, you know, and then you change your Runge-Kutta method, you should be able to use that, okay? Remember we were changing beta and how we were using that, so that was very interesting, isn't it? So that, and again here, as we are able to express, we have done this earlier in this particular case also, so we are able to express, for example, the velocity and the boundary layer thickness, right, in terms of a local zeta, okay, and therefore from there we are able to, you know, obtain values for the Nusselt number, Ralph's number, and the temperature profile. Okay, so similarly, when you have these cases, so all you basically need to do is make sure that you change the, you know, and one of the fun things to do, as I showed you, you know, in one of the modules, is to just keep changing these values and see what you get, right? So I think that's the first step one would do. You just, you know, build up a code and keep changing things and see how things are changing and all that, and slowly, once you sort of said, okay, fine, now I've played enough, now let me go and do this. So let's take a particular case where, say, for example, you know, I have something like this, fluid convergent channel. So alpha 1 is 0, alpha 2 1, alpha 4 is minus r, right? And then try to interpret the velocities and the output that you get, you know, the temperature output that you get in terms of the actual physical flow in a convergent channel. So that really is the objective. So one more thing that I wanted to impress upon here, so this is here, so boundary layers with a wall. So you actually have a physical wall, right, on which the boundary layer is developing, right? So that's what we mean. So whether it's a wedge, you know, it's a wedge like that, and you have a boundary layer, sorry, not that way, okay? All right, so not that way. So you actually have solid surface like that and solid surface like that, and then you have boundary layers forming, right? So that's a wedge, and you know, and of course you have a convergent channel, so then you have boundary layers forming, right? So obviously, so this is a channel So boundary layers are forming on the inside here, right? Then you have a moving flat plate. So you have a flat plate which is moving. So then there's a boundary layer forming. So there is, and then of course there's a wall jet. So there is actually a a solid wall, on which the boundary layer is forming. This is more intuitive. This is what we've been doing, flat plate and things like that, right? Now the boundary layers without a wall. Now that is kind of almost like a misnomer, right? You're like, how can a boundary layer form without a wall? Well, I think, you've also heard of immiscible fluids, immiscible liquids. So you have like, water and oil. So they will not mix, right? They will not mix and they form a layer which is basically the boundary. So therefore, in this case, if you see the boundary conditions, right? So again, for these constants, these constants will change, right? And the boundary conditions, for example, if you see, then that changes. So if you see the boundary conditions, this goes from the, so if you have, for example, this is one fluid, right? I'm kind of exaggerating this a little bit, okay? And right, and you have another fluid here. Right? So this is a fluid and we got this fluid in here. Right? If you got something like that, so the boundary conditions is, so it goes from essentially, from here, so negative, far off from this end where the non-dimensional, temperature difference is this, and then it goes to the other end, where the theta is 0. So since there is no like solid wall or whatever, so basically then we're saying, and then this here, so this is the parallel jet, so the temperature, is there is a certain temperature difference there. So right, so therefore again, similarly for the free jet, right? So and you could actually have these two fluids, it could be at a different temperature. So you could, if they could be at different temperatures, right? So right, so if for example, yes, so that's basically boundary layers. It's without a wall, because if you want to think about it, say for example, this is honey, okay, this is honey, and this is say water. Okay, and it would probably want to flow. So obviously, just think about what should happen if something like this is going on. If the water comes in here, I think it's also you could think about how that would look like. If you have a thick layer of honey and you allow throw a little water on that, how will that how will the velocity look like? Will it flow as nicely, as freely, or as you would expect it to flow over, any other, say, a smooth floor, or for that matter, would it be the same or different compared to if we were to just say throw water on a flat table like that? Okay. So anyway, we haven't done this exactly in detail. So boundaries without a wall. I just wanted to sort of give you an overview of the whole thing. So all of this. So, but there's something to think about, especially for people who want to do research and things like that. Something to think about that, how this thing will develop. But the whole idea of all of this is that the computer code doesn't know all that. It doesn't know whether you think there is water or honey and whatever. It doesn't know all of that. So all you have to tell the computer code is take this alpha 1, alpha 2, alpha 3, alpha 4, right? Give it these boundary conditions, okay? And look at the results and look at the output and see some inferences from there, okay? And that should give you a lot of inferences about, what I just asked, what I just said, that how will the velocity profile look like? Well, you can actually, if you get an output from this computer code, you should be able to see that, how a velocity boundary layer is behaving, or how the thermal boundary layer is behaving. Okay. So similarly here, for the free jet, you have several conditions, and yes, well, eigen solution, hot free jet, etc. So Well, we kind of, what I mean by this, the thermal energy in the free jet must be independent of the distance along the jet. Well, I guess, we don't see the energy packet kind of changing as it moves along, as you move along the jet. We don't want that to happen. So we kind of assume that it is, it's independent of the distance that it moves along the jet. So, okay, like I said, I haven't really done this in detail, but this is just to give you an idea that if you have a basic code in place, you can still sort of run the code, and get some results and see some output from that. That doesn't stop you from doing this, and it's a doable thing. I've given you, an idea of how the code works, and you can actually make that work. So it should be interesting to see how you should be able to do that. Okay, so I think I'll go ahead and stop here, okay, and hopefully we will talk about something interesting at another time. So, well, thanks.